Are you confused about the difference between big O of n squared and big O of 2 to the power of n? You're not alone. This is a common question that many people have when diving into algorithm analysis. I totally get it. It can be really frustrating when you're trying to understand how these complexities work, especially when you read something that seems contradictory. You're definitely not the only one who feels this way. Let's look at the specific question that sparked this discussion. One user asked, why does O of 2 to the power of n plus n to the power of 100 reduce to O of 2 to the power of n? They were puzzled because for n equal to 3, n to the power of 100 seems to have a higher count of executions. Sound familiar? Let's break this down. So what's going on here? The key lies in understanding how big O notation works. Big O notation describes the upper limit of an algorithm's running time as the input size grows. While n to the power of 100 may seem larger for small values of n, it grows much slower than 2 to the power of n as n increases. And stick around. At the end of this video, I'll share a simple way to visualize these complexities that will make it all click for you. To clarify the confusion about big O notation, let's first understand what big O represents. Big O notation describes the upper limit of the time complexity of an algorithm as the input size grows. In the expression O of 2 to the power of n plus n to the power of 100, we need to compare the growth rates of the two terms as n increases. The term 2 to the power of n grows exponentially, while n to the power of 100 grows polynomially. As n becomes larger, the exponential term 2 to the power of n will dominate the polynomial term n to the power of 100. This is why we can drop the insignificant part when expressing the overall complexity. For example, if n equals 3, 2 to the power of 3 equals 8, while 3 to the power of 100 is a very large number. However, as n increases further, 2 to the power of n will eventually surpass n to the power of 100. In conclusion, when analyzing algorithms, we focus on the term that grows the fastest as n increases. In this case, the user can confidently say that O of 2 to the power of n is the correct simplification. Fun fact, the term big O was coined by mathematician Paul Bachmann in the late 19th century. It's amazing how a concept from so long ago is still so relevant today. Now let's look at the answers provided by other users. This user clarifies that big O notation describes asymptotic complexity, meaning we consider n as infinitely large. Although n to the power of 100 grows faster initially, eventually 2 to the power of n will surpass it. That's the end of that answer. Let's see another perspective. This user clarifies that big O notation focuses on asymptotic complexity. They explain that as n approaches infinity, the limit of 2 to the power of n divided by n to the power of 100 approaches infinity. This means that 2 to the power of n grows significantly faster than n to the power of 100. That's the end of that answer. Let's see another perspective. This user clarifies that when evaluating complexity, we should consider all possible values of n, not just a single example. They explain that for larger values of n raised to the power of 100 becomes insignificant compared to 2 raised to the power of n. Here's a tip. When analyzing algorithms, always consider how they behave as n approaches infinity. This perspective will help you understand why certain terms can be dropped. And there you have it. Understanding big O notation can be tricky, but with practice, it becomes clearer. If you found this video helpful, please subscribe for more insights, and remember to keep questioning and exploring.